Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point and you will not miss a thing. Tonight we are going to talk about weather, slowly, without hurrying. Long before anyone thought to seal mercury in a glass tube and watch it rise, the weather was read with the eye, the ear and the skin, by people who had no choice in the matter. A harvest brought in a day too late, a fishing boat that put to sea on the wrong morning, a flock left on high pasture when the snow came down. The cost of misreading the sky was immediate and personal, and so the reading was practiced with great care and passed on in forms that could be remembered without writing. Rhymes, proverbs, a habit of glancing westward at a particular hour, an ingrained sense of what the wind ought to be doing in that month, and what it meant when it did something else. Farming societies fixed the broad shape of the year to the sky rather than to the weather itself, since the stars were reliable in a way the clouds were not. Hesiod, writing in Greek in a poem of advice to a brother about work and the seasons, tells his reader to begin the harvest when the Pleiades rise before dawn, and to plough when they set. And this joining of a star pattern to a task belongs to a very old habit of thinking. Egyptian farmers watched for the reappearance of Sirius near the season of the Nile flood. Such rules were not forecasts in the modern sense, more a calendar written on the night sky. But they gave the year its frame, and the day-to-day guesswork happened inside it. Weather law was intensely local, and this was its strength as well as its limit. A fisherman on one stretch of coast knew that a certain haze on a certain headland meant wind by evening, and that knowledge was of no use 40 miles away. Valleys had their own fogs, their own funneling winds, their own hills that snagged rain out of a passing cloud, and a lifetime of watching one small piece of ground produced a body of predictive skill that no traveller could carry off. Herders on high summer pasture learned the hour at which the daily cloud began to build over a particular ridge, and the difference between the day it built early and the day it did not. Wind was the master sign, more trusted than any other, because a shift in its direction is the plainest outward mark of a change in the larger pattern of the air. Along the western edges of Europe, sailors and farmers alike knew that a wind coming steadily from the southwest carried warmth and wet off the ocean, that an easterly in winter brought hard, cold and clear nights, and that a wind swinging around through south and then west in the course of a day belonged to a sequence of rain that would end in bright, showery air. That sequence has a modern name and a modern explanation involving the passage of a depression with its boundaries of warm and cold air. But the sequence itself was known and relied upon for centuries by people who described it only as the wind going round. Cloud shape gave a longer warning, sometimes a day or more, and the sharper observers learned to read it as an order of events rather than a single omen. High feathery streaks appearing in an otherwise clear sky, thickening into a whitish veil through which the sun still shows as a pale disk, then a lowering greyness, then rain that begins as a drizzle and settles in. This is the ordinary approach of a warm front seen from the ground, and it was catalogued in proverb long before it was catalogued in science. Sailors watched the same procession from the deck and gave it the same weight, since the first thin streaks arrived while the sea was still calm, and the barometer, once they had one, had barely begun to fall. Halos around the sun or the moon belong to this same sequence, and the old rule that a ring around the moon means rain has a straightforward physical basis. That ring is produced by sunlight or moonlight, refracting through hexagonal ice crystals in clouds so high and so cold that it is made of ice throughout, and such cloud very often forms the leading edge of an advancing frontal system, so that the halo appears roughly half a day to a day before the rain. Not every halo is followed by rain, since the high cloud can pass with nothing behind it, but the association is real and not coincidence, which is more than can be said for a good deal of traditional lore. A sky broken into small rippled patches, called a mackerel sky for the pattern on the fish, was taken as a sign of unsettled weather. And here too the reading holds up reasonably well, because those regular cells form where the middle atmosphere is moist and slightly unstable, conditions that often precede a change. Tall clouds with hard cauliflower tops growing through a summer afternoon warned of thunder, and the flattening of such a top into a spreading anvil shape told an experienced watcher that the storm had reached its full height and was already producing hail or heavy rain somewhere beneath it. Color at dawn and dusk carried a reputation older than any written meteorology, most familiar in the couplet about a red sky at night, delighting the shepherd, while a red sky in the morning gives warning. When the sun is low, its light travels a long slanting path through the atmosphere, and the shorter blue wavelengths are scattered away, leaving reds and oranges to reach the eye, so that a deep clear red at sunset means the air to the west is relatively free of thick cloud. In the middle latitudes, where weather systems generally travel from west to east, clear air in the west is tomorrow's air, and a glowing red dawn means instead that the clear gap has already gone past and the cloud is arriving. The rule works where the prevailing motion of the atmosphere makes it work, and fails where it does not, which is why versions of it are strongest in European and North American tradition. Animals were watched closely, partly with good reason and partly out of hopefulness. Swallows and martins feeding low over a meadow before rain are following insects that fly lower when the air is heavy with moisture and the pressure is falling. And the behavior of bees returning early to a hive has a similar practical explanation. Frogs and toads call more insistently in damp, warm air. Cattle lying down in a field, on the other hand, has never been shown to predict anything much, since cattle lie down for many reasons and spend a large part of any day doing it, and the belief survives mainly because a person who already suspects rain will notice the herd and remember it. Plant material made a serviceable instrument without anyone intending it as such. Pine cones open their scales in dry air and close them as humidity rises. Seaweed hung by a doorway turns limp and clammy before wet weather, and dry and crisp before fine. And ropes, wooden doors and human hair all take up water from the air and change their length or their behavior accordingly. Salt clumps in the cellar, smoke from a chimney that lifts straight up indicates the air is unstable and pressure is likely high, while smoke that hangs and spreads sideways is trapped beneath a layer of warmer air overhead. All of these respond to real physical properties, and each would later be measured properly by a device built on the same principle. Sound and smell were part of the reading too. Distant noise carried unusually clearly, so that bells or a waterfall could be heard from farther than normal, indicates that sound waves are being bent back down towards the ground by a layer of warmer air aloft, and the earthy scent that arrives just ahead of a summer shower comes partly from compounds released by wet soil and partly from oils that plants leave on dry ground, lifted and spread by the first gusts of the downdraft. Aching joints and old injuries before a storm are harder to judge. Falling pressure and rising humidity plausibly affect tissue, and many people report the connection with confidence. But attempts to measure it have given mixed and modest results. Collections of such signs were written down early. A short Greek treatise on weather signs, attributed in antiquity to Theophrastus, gathers dozens of them from farmers and sailors, and Aristotle's work on things in the air attempts explanations for winds, clouds, and halos within the physics of his day. Virgil devoted long passages of his poem on farming to the reading of storms, and Pliny compiled further signs among his vast notes on the natural world. Later, printed almanacs sold such rules in bulk, mingling sound observation with astrological prediction, and an 18th century English collection of Shepherd's rules for judging the weather went through many editions, which tells us less about its accuracy than about the appetite for guidance. Much of that inherited body of rules did not survive examination. Beliefs tying the weather to the phase of the moon or to the saints' days on which rain would supposedly continue for a fixed number of weeks turned out, under counting, to hold no predictive value. And the same is true of most attempts to read a whole season from a single day. The signs that endured were nearly all short range, reaching hours ahead rather than months, and nearly all concerned with the present state of the air rather than with hidden influences. When instruments arrived, they did not replace this way of seeing so much as sharpen it, giving numbers to the heaviness, the dampness, and the pressure that generations of observers had already learned to feel. Clouds were among the last ordinary things in the sky to receive names that could travel. Every language had words for them, and often beautiful ones, drawn from fishing and farming and the look of animals, so that a certain rippled sheet of high cloud was a mackerel sky along one coast, and something else entirely along the next, and the long fibrous streaks were mares' tails to some observers and brushed hair to others. Such words worked well among neighbors and failed at any distance. Botanists and mineralogists by the end of the 18th century had orderly systems, each plant and each crystal fixed in a scheme that a stranger could consult, while the shapes of the air remained outside all that, dismissed by many as too fleeting to be sorted, since a cloud might change its whole appearance in the time it took to write a description of it. The man who altered this was a London chemist of modest public standing, Luke Howard, born in 1772 into a Quaker family, schooled at a friend's school in the country, apprenticed to a retail chemist, and afterwards a partner in a business that manufactured and supplied drugs. Meteorology was what he did outside trade. He watched the sky in the early morning before business hours and in the evenings after them, and he kept written records with a persistence that lasted decades. Accounts of his life connect the beginning of that interest to the strange skies of the summer of 1783, when a dry volcanic haze spread from Iceland across Europe, dulling the sun and reddening the horizon for weeks, and when a brilliant meteor crossed the country and was described by observers in many towns. In December of 1802, at a meeting of a small London society whose members gathered to read papers to one another and to try experiments with gases, Howard read an essay he called an account of the modifications of clouds. The society was informal, the audience numbered perhaps a dozen, and the paper was printed the following year in a scientific magazine of the day, illustrated with soft engravings after Howard's own sketches. Nothing about the occasion suggested that the vocabulary offered that evening would still be in use 2 centuries later in aviation reports and school textbooks, and the ordinary speech of people who have never heard the name of its author. 3 words carried the scheme. Cirrus, from the Latin for a curl or a lock of hair, described the highest clouds, fibrous and drawn out, forming no compact mass. Cumulus, meaning a heap, named the piled convective clouds that grow upward through the middle of a warm day, dense at the edges and flat below. Stratus, from the verb for spreading out, was reserved for the low sheet that forms in the calm of evening and lies in layers rather than in heaps. To these Howard added nimbus for the rain-bearing cloud, and a set of compound names for the forms that stood between the simple ones, joining the roots into cirrocumulus, cirrostratus, and cumulostratus, so that a single observer could report gradations rather than being forced to choose among 3 boxes. Calling them modifications rather than species was deliberate, and it mattered more than the individual names. Howard argued that cloud shapes are not fixed kinds, but stages in a process, the visible result of water condensing and evaporating within moving air, and that one form passes into another in ways an attentive watcher can follow. He described the heaped cloud of afternoon spreading and sinking into a level layer as the ground cooled, and the high fibrous streaks thickening into a pale sheet through which the sun shows as a bright patch, a sequence that often precedes rain by a day. The classification therefore made a physical claim as well as a linguistic one. Shape was evidence of process, and a name for the shape was a shorthand for what the air was doing. Latin was chosen so that the terms would belong to no country and offend no ear, following the practice that had already served natural history well, and the choice proved decisive. During the same years, a French naturalist of considerable reputation had proposed his own cloud classification, published in a series of annual meteorological volumes, using descriptive French phrases for hazy clouds, flocked clouds, and grouped clouds. These names were vivid to French readers and awkward to everyone else. They appeared in publications of limited circulation, and they did not spread. Howard's scheme, being made of roots that a German, a Swede, or an Italian could pronounce and recognize, was adopted piecemeal by whoever needed it, which is how a private essay by a manufacturing chemist became the international language of the sky. Goethe in Weimar encountered the classification in a German rendering some years after its publication and took it up with real enthusiasm, since he had long been keeping his own notes on weather and had felt the want of terms. He composed verses in honor of Howard, treating the 4 principal forms in turn, and he asked, through correspondence, for information about the life of the Englishman who had named them, receiving in reply a modest autobiographical account. Through Goethe, the words reached German literary and scientific circles at once, and through the popular scientific books of the period, which reprinted and explained the categories for general readers. They reached a wider English audience than the original essay ever had. Some writers proposed plain English substitutes for the Latin terms, homely compounds meant to be easier on the untrained ear, and these found almost no use. Painters were among the readers. In the early 1820s, John Constable spent long stretches on Hampstead Heath making rapid oil studies of sky alone. And on the backs of many of them, he wrote the date, the hour, the direction of the wind, and a few words about the weather, treating each sketch as an observation as much as a picture. He owned a copy of one of the books that carried Howard's terminology to a general public, and the habits of the two men rhyme even where the influence is hard to measure precisely, since both were trying to record a state of the air accurately enough to be compared with another state on another day. Poets of the same generation wrote of clouds changing form without dissolving, an idea that sits close to Howard's central point. By the middle of the century, national weather services were collecting reports from hundreds of observers, and the loose use of terms had become a practical nuisance, since one man's stratus was another man's fog, and the compound names were applied inconsistently from station to station. A Swedish meteorologist at Uppsala began using photographs as the standard of reference, which removed much of the ambiguity that words alone had left. And a British observer who had travelled widely by sea reported that the same cloud forms recur in every part of the world, so that a single vocabulary could reasonably be made to serve all latitudes. International committees took the matter up in the 1880s and 90s, and the first International Cloud Atlas appeared in 1896, a slim volume of coloured plates and text setting out 10 principal types, arranged by height and built on Howard's roots. Later editions enlarged the system considerably, borrowing from biology the ranks of genus, species, and variety, so that a cloud could be described in 3 or 4 terms according to its family, its shape, and its transparency or arrangement. Names for the middle level of the atmosphere were formed with the prefix alto, giving altocumulus and altostratus, and Howard's nimbus was retired as a genus in its own right. Its work divided between nimbostratus for the deep grey rain sheet and cumulonimbus for the tall storm cloud with its spreading top. Revisions followed through the 20th century, one of them running to 2 volumes with photographic plates. And in 2017, the atlas was reissued as an online reference, adding, among other things, a name for the long horizontal roll cloud and a category for clouds formed by human activity, such as those trailing from aircraft or rising from cooling towers. Howard's original words survived all of this almost unchanged, which is unusual for a scientific vocabulary of that age. Their durability owes something to the sound of them, and more to what they made possible. Because once a form had a name that meant the same thing in 2 hands, entries from different places and different years could be laid side by side and counted. A sky described as cirrus over Norfolk in 1820 could be compared with a sky described as cirrus over Bengal in 1890. And comparison of that kind is the beginning of every generalization about weather that has since been made. Air offers nothing solid to lay a ruler against, no surface to mark, and no edge to pinch between finger and thumb. And for most of human history, the qualities of a day could only be reported in words that shifted with the speaker, since one person's mild morning was another's chill, and a wind called strong by a gardener would have seemed moderate to a fisherman. What changed between the early 17th century and the middle of the 19th was not the weather, but the arrival of small pieces of glass and brass and wood that answered a question with a mark on a scale, and the marks could be copied into a book, sent in a letter and set beside marks made 100 leagues away by somebody the writer had never met. Each of the 4 principal instruments took the same path from curiosity to standard. Heat came first, in Italy, around the beginning of the 1600s, in the form of a bulb of glass with a long neck standing in a dish of water, so that as the trapped air warmed and expanded, the water in the neck sank, and as the air cooled, the water rose. Galileo is associated with the earliest of these devices, and a Venetian physician of the same period, Santorio, put versions of them to work in medicine, watching a patient's warmth rather than judging it by touch. Such instruments responded to temperature honestly enough, but they were open to the atmosphere and therefore also responded to pressure. And since every maker cut his own scale according to his own marks, 2 of them in the same room could disagree without either being wrong. Sealing the liquid inside the glass solved the first problem, and that step is credited to the workshops of Florence in the middle of the century. Under the patronage of Ferdinand II, Grand Duke of Tuscany, whose glass-blowers made slender stems filled with spirit of wine and marked with tiny fused beads for degrees. The Grand Duke also did something less often noticed and more consequential, in that he had a number of these thermometers made to match, distributed them to observers in several Italian towns and to a monastery or 2, and asked for readings at fixed hours, which produced the earliest set of temperature records that can be compared across places because the instruments themselves had been compared first. Comparability across generations required fixed points, agreed states of matter that anyone could reproduce, and the freezing and boiling of water were the obvious candidates once it was understood that both occur at steady temperatures under steady pressure. Fahrenheit, working in the Netherlands in the early 18th century, made mercury thermometers of remarkable consistency and fixed his scale with a salt and ice mixture near the bottom and blood heat well up the stem. Réaumur divided the interval between freezing and boiling into 80 parts. Celsius, in 1742, proposed 100 divisions between the same 2 points, though in his arrangement 0 marked boiling and 100 marked the melting of ice, and the order was reversed by others soon after his death, in the form still used across most of the world. A century later, the thermodynamic scale was defined, its 0 placed where a gas would exert no pressure at all. Exposure mattered as much as calibration, a lesson learned slowly and by irritation, because a thermometer in sunlight reports the temperature of the thermometer. One against a wall reports the wall, and one in still air inside a box reports the box. Observers experimented with north-facing walls, open sheds and metal shields, and in the 1860s, a Scottish engineer, Thomas Stevenson, settled the matter with a white wooden box on legs, its sides made of double louvres to let air pass while excluding sun and rain and sky radiation. That design, in various sizes, went on to stand in gardens and enclosures around the world. And its dimensions are part of the reason a temperature recorded in one country can be set beside a temperature recorded in another. Weight of air was measured almost by accident, out of a practical puzzle concerning pumps, which drew water up a pipe readily to about 10 meters and then no further, no matter how sound the leather or how strong the arm. Torricelli in 1643 reasoned that the pump did not pull the water so much as the outside air pushed it, and that a denser liquid would therefore stand in a shorter column. So he filled a glass tube about a meter long with mercury, stopped the end, inverted it into a basin, and watched the mercury fall until roughly 76 centimeters remained standing, with an apparently empty space above it. The height of that column varied slightly from day to day, and the variation was the first hint that the thing being measured belonged to the weather. 5 years later, the argument was carried up a mountain in central France, where Pascal arranged for his brother-in-law Perrier to take a mercury tube to the summit of the Puy de Dôme, while a second tube was watched at the foot. And the mercury on the summit stood some 8 centimeters lower than the mercury below. Air, then, had weight. The column stood in proportion to the weight of the air above it, and going up through the atmosphere meant leaving part of that weight behind. From this, the barometer acquired 2 careers at once, as a measurer of height and as an indicator of the state of the atmosphere at a fixed place. Weather glasses spread quickly through the houses of those who could afford them, often with words such as fair and change and stormy engraved around the scale. And though the words were crude, the underlying association held, since a falling barometer commonly precedes wind and rain, and a high steady reading commonly accompanies quiet weather. Instrument makers improved the reading rather than the principle, Hooker devising a wheel mechanism to turn small movements of mercury into a swinging pointer, and later makers narrowing the tube and adding gimbals so that the instrument could be used at sea without the mercury pumping wildly with the ship. In the 1840s, a French inventor, Vidier, patented the aneroid, in which a shallow sealed metal box with a partly evacuated interior flexed with pressure and drove a needle through levers and a chain, giving a portable instrument that needed no mercury at all. Serious use brought corrections with it for the expansion of mercury with heat, for the slight difference in gravity between latitudes, and above all for altitude, since readings from stations at different heights must be reduced to a common level before they mean anything side by side. Moisture proved the most stubborn of the 4 to pin down. A German cardinal of the 15th century suggested hanging wool from a balance and watching it grow heavier in damp air, and Leonardo sketched something similar, and both were right in principle while offering no number anyone could repeat. Later experimenters looked for materials that changed length rather than weight, trying gut, whalebone, paper and the beard of an oat, until in the late 18th century Horace Benedict de Saussure in Geneva built a hygrometer around a single human hair, degreased and stretched over a pulley with a light weight, its lengthening in damp air turning an index across a dial. Such instruments drifted with age and needed frequent checking against saturated air and against air dried over a salt. But they made humidity a quantity rather than an adjective. The method that eventually prevailed rested on evaporation, since water evaporating from a wet surface takes heat with it and cools that surface by an amount that depends on how much moisture the surrounding air already holds. 2 matched thermometers mounted side by side, one with its bulb kept wet by a muslin wick and the other left dry, therefore differ by a wide margin in dry air and hardly at all in saturated air, and a German physicist in the 1820s gave this pairing the name psychrometer. Tables were computed and later refined by careful laboratory work on the vapor content of air, so that the two readings could be converted into a dew point or into the ratio of the moisture present to the maximum the air could hold at that temperature, which is what a report of humidity as a percentage still means. Rainfall needed no glassblower, only a vessel of known mouth and the discipline to empty it on schedule, which is why measurement of rain is older than measurement of heat or pressure by a considerable margin. A treatise on statecraft from ancient India describes gauging the rain of a district for the assessment of taxes. And in Korea in the 1440s, standard bronze vessels were cast and sent out to provincial offices with instructions on the depth of water to be recorded after each fall, producing an administrative rainfall record of real length. In 17th century England, Wren and Hooke worked on a self-emptying gauge linked to a clockwork register, and a Lancashire gentleman, Richard Townley, kept monthly rainfall totals for years together, giving the beginning of the long series that later observers extended. Simplicity in a rain gauge is deceptive, because the funnel must be sharp-edged and level to define its collecting area exactly. The water must fall into a narrow-necked bottle or a deep can so that little of it evaporates between visits, and the whole must stand where wind is not accelerated over its mouth, since air lifting over the rim carries small drops past it, and a gauge set high on a wall may catch a quarter less than one set in a sheltered pit. Snow demands melting before it can be measured at all. National services eventually settled on standard diameters and standard heights above the ground, and in Britain from the 1860s, a private organization for the collection of rainfall observations gathered returns from hundreds and then thousands of volunteers, checked their gauges, and published the totals in annual volumes, turning a scatter of buckets in gardens into a map of where the rain fell. A number written once means very little, because a temperature of 9 degrees or a pressure reading taken on one particular afternoon says nothing about whether that afternoon was ordinary or strange, and the worth of any measurement of the air lies almost wholly in its neighbours, in the reading of the day before and the day after, and in the same date recorded across a run of other years. The instruments described so far became knowledge only when somebody agreed to attend to them at the same hour each morning, in health and in bad temper, on holidays and during visits, and to write the result in a book that would not be thrown away. That habit, unglamorous and easily broken, turned out to be the foundation of everything later known about the climate. Some of the earliest surviving evidence of the habit comes from a clerk in 14th century England named William Merle, who kept a record of the weather in Latin for 7 years, month by month, noting rain and drought and frost, and the character of the winds in a manner that already resembles a register rather than a chronicle. He had no instruments and could give no figures, so his entries describe conditions in words. Yet the discipline is recognizable, and the manuscript shows a mind interested less in individual storms than in the sequence of ordinary days. Whether he intended a scientific record or an aid to prediction is not clear from the pages themselves. Monastic houses and landed estates produced a great deal of writing that was not meant as weather observation at all, but has since been read as such. Chronicles record when the vines froze, when a river ran dry, when floods carried away a bridge, when processions were held to ask for rain, and when the harvest came in early or failed. Account books record the price of grain and the cost of repairing roofs after gales. None of this is measurement, and each entry carries the bias of whoever thought the event worth remarking on. Yet across many hundreds of documents from many places, the pattern of unusual seasons can be traced backwards well beyond the age of the thermometer. More precise still are the records that fixed a date rather than described a condition. In Japan, court diaries and temple registers noted for centuries the day on which the cherry trees flowered in Kyoto, because the flowering governed a season of poetry and ceremony, and the resulting series of dates now stands as one of the longest indications of spring temperature anywhere. Shrine officials at Lake Suwa recorded each winter whether and when the ice closed over the water, a matter of ritual observation rather than science. In northern Sweden, the breaking of the ice on the Torne River was written down from the late 17th century onward. Burgundian towns kept the day on which the grape harvest was permitted to begin, a decision made by committee and recorded in municipal registers, and the sequence of those dates responds to the warmth of the growing season with surprising sensitivity. Deliberate weather journals in the modern sense began to appear once the instruments existed to fill them. Robert Hooke set out a scheme for what he called a history of the weather, proposing a ruled page with columns for the day, the wind's direction and strength, the temperature, the pressure, the amount of moisture in the air, and a further column for the general appearance of the sky, with abbreviations to be used so that entries stayed short and comparable. The layout mattered as much as the content, since a table invites completion in a way that prose does not, and a blank cell announces itself as a failure of attention. Tycho Brahe, on his island observatory in the late 16th century, had his assistants note the weather daily alongside the astronomical work, partly because cloud determined what could be observed and partly from a general interest in the air, leaving a register of several years. John Locke kept a weather account for a time with instruments lent by a friend, entering pressure and temperature and wind in a small hand. Across the following century, the practice spread among clergymen, physicians, country gentlemen and schoolmasters, people whose lives were fixed to one place and one routine, which is exactly what a long record requires. Thomas Barker at Linden Hall in Rutland kept observations for a remarkable span of decades in the 18th century, recording pressure, temperature, rain and wind with a consistency that later climatologists have relied upon heavily. He was connected by marriage to Gilbert White of Selborne, whose own naturalist's journal set the weather of each day beside the first swallow, the flowering of particular plants, the behavior of insects and the state of the crops, so that the natural year and the meteorological year appear on the same line. White's pages show something the tables alone cannot, which is how weather is experienced by everything living in it. An attempt at coordination on a larger scale came from Mannheim in the 1780s, where a learned society organized what may fairly be called the first international observing network. Matched instruments were distributed to observers scattered from Western Europe to Russia and across to North America, with instructions on where to place them and at which hours to read them, the readings being taken 3 times a day at fixed times, so that entries from different countries could be laid alongside one another. The society published the returns in annual volumes. Its life was short, cut off by war and the dispersal of its members, but the principle it demonstrated, that identical instruments read at identical hours in many places, yield something no single diary can, was not forgotten. At sea, the diary had a different origin, since a logbook was a legal and navigational document rather than a scientific one, and the weather went into it because a ship's position depended on the wind. Officers entered the wind's direction and force, the state of the sea, the sails carried, the rain or fog encountered, and the readings of whatever instruments were aboard, usually at set intervals through the watch. Naval and merchant archives, therefore, hold millions of such entries covering the great sailing routes over several centuries, and modern projects have transcribed them by the hundreds of thousands, often with volunteers reading the handwriting page by page to recover the winds of oceans nobody now alive has crossed under sail. Luke Howard, whose cloud names had already entered general use, spent years keeping a daily register in and around London and published the results as a study of the city's climate. And among the things he noticed was that the town was reliably warmer than the country around it, particularly at night. He did not have the vocabulary of the urban heat island, but the effect was in his figures, and it had been found by nothing more elaborate than reading the same instruments in two kinds of place for long enough to be sure. Turning such collections into climate required a further and less obvious labor. A record that runs for 300 years has almost never been made in one way throughout. Thermometers were moved from a north wall to a louvered screen. The hours of observation changed. An observer died and a successor took over with a different instrument. A town grew up around a station that had once stood in fields. Each of those changes leaves a step in the series that has nothing to do with the atmosphere. The work of homogenization compares each record against its neighbors, hunts through letters and station histories for the dates of moves and replacements, sometimes reconstructs old exposures to measure how much they differed, and adjusts accordingly. From that patient reconciliation of English diaries came a monthly temperature series for central England reaching back to the middle of the 17th century, which remains the longest instrumental sequence of its kind. What such series revealed was that climate is not fixed. The cold decades that let fairs be held on the frozen Thames appear in them, as does the failure of summer in the year following a great volcanic eruption in the East Indies, and so does the slower warming of recent times. None of it could have been recovered from memory or from chronicles alone. It exists because a long succession of people, most of whose names are known only to archivists, considered it worth walking out to a garden before breakfast to look at a thermometer and write down a figure that seemed, on the day, to be of no interest whatever. At sea, the wind mattered more than anything else that could be measured, and yet it was the thing described most loosely. A mate might write in the log that the breeze was fresh or stiff, or that it blew a hard gale, and the words meant whatever his own years of experience had taught them to mean, which was not necessarily what they meant to the man who had trained on a different coast in a different trade. Two ships, lying within sight of each other, could record the same afternoon in terms that would not have been recognized as the same weather by anyone reading the two books side by side. For navigation, this hardly mattered, since the officer wrote for himself and for his owners. For anyone hoping to compare one ocean with another, it mattered a great deal. Francis Beaufort, an officer of the Royal Navy who later held the post of hydrographer to the Admiralty, addressed the difficulty in his own private journals in the first decade of the 19th century. By numbering the wind, his scale ran from 0, which was calm, to 12, and each step was defined not by an instrument but by what a well-found ship of war could carry in the way of canvas. In the lightest airs, she could spread everything she had and would barely move. As the wind rose, she carried all plain sail comfortably, then began taking in her upper canvas, then reefed her topsails once and twice, and finally close-reefed them, until at the highest numbers she could show no canvas at all, and simply endured. The definition was practical, shared, and independent of any glass or dial that might be broken or left ashore. What made that arrangement work was also what eventually dated it. Sail gave way to steam, wooden hulls to iron, and a description written around the rigging of a frigate meant nothing to an engineer on a collier or to an observer standing on a headland with no ship in sight. So the numbers were rewritten in terms of the surface of the sea itself, a mirror surface, then scale like ripples without crests, then small wavelets with glassy crests that do not break, then crests beginning to break with scattered white foam, then whitecaps in numbers, then spray blown from the tops, then foam drawn out in streaks along the direction of the wind, and at the extreme an air so filled with spray and foam that visibility fails. The Royal Navy directed the use of the scale in its logs in the later 1830s, and the International Meteorological Committee recommended it for general use in the 1870s, by which time it had become the common language of wind at sea. Alongside such judgments by eye, there were instruments, and they grew slowly more reliable. Pressure plates hung in the wind gave a crude force. The cup anemometer, devised in the middle of the century by an Irish astronomer, turned steadily in any horizontal wind and could be geared to a counter so that the average speed over an hour could be read as a distance of air passed. Speed at sea was already being measured in knots, a word that came from the practice of paying out a line with knots tied along it at set intervals while a small sand glass ran, counting the knots that went over the rail. When wind speed equivalents were finally attached to the Beaufort numbers in the early 20th century, they were fitted to the descriptions rather than replacing them, and the descriptions survived precisely because a trained observer could apply them from a moving deck without touching an instrument at all. Every ship kept a log, and the log was a legal and commercial document long before it was a scientific one. Course steered, distance run, sail set, the direction and force of the wind, the state of the sky and sea, and often the temperature of the air and of the water were entered watch by watch. Such books were preserved in naval offices, in the archives of trading companies, and in the counting houses of ship owners, not for their weather, but for evidence in disputes about cargo and delay. The consequence was that the world's oceans, where no observer stood and no station could be built, had nevertheless been sampled millions of times. Along every route that commerce found worth sailing, in a form that nobody had yet thought to add up. In Washington, an American naval officer whose sea service had been ended by an injury ashore took charge of the depot of charts and instruments and began that addition. Matthew Fontaine Maury set clerks to work stripping old logbooks of their weather entries and sorting them by position, dividing the oceans into squares of latitude and longitude and assembling, for each square and each month, the winds that ships had actually met there. Out of that came the wind and current charts, published from the 1840s onward, which showed by little arrows and figures the prevailing direction, the frequency of calms, and the likelihood of gales in each patch of sea. Maury then made the arrangement circular. Captains who returned completed observation forms received the charts in exchange, so the record fed on itself and grew. From those plotted squares came sailing directions, and the directions could be tested against the clock. Vessels bound south from North American ports had long crossed the equator by habit and often lost weeks in the belt of calms. The charts suggested where the belt was narrowest by season and where the trades could be picked up soonest, and average passage times to Brazil and around the southern tip of South America fell noticeably for ships that followed the advice. Ship owners, who cared nothing for atmospheric circulation, found that they cared very much about the saving of weeks. And the standardized forms went out by the thousand. Delegates from the principal maritime nations met at Brussels in 1853 to make the practice common property. What they agreed was modest and consequential. A uniform abstract log, the same categories entered at the same hours by ships of every flag. Instruments compared against one another so that a thermometer aboard a Dutch bark could be trusted against one aboard an American clipper, and an understanding that the returns would be pooled rather than hoarded. Britain established a small department under the Board of Trade to receive its share of the observations, and other governments made similar arrangements. That conference is usually counted the beginning of international cooperation in meteorology, and its subject was not storms over land, but the wind over water. Slowly, out of arrows drawn on paper, the general circulation of the lower atmosphere took shape as a permanent structure rather than a series of local habits. The trade winds appeared as broad belts blowing steadily toward the equator from the northeast in one hemisphere and the southeast in the other, separated by a zone of calms and squalls that shifted north and south with the season. Beyond the trades lay latitudes of light and variable airs, and beyond those the westerlies, strengthening in the Southern Ocean into the persistent gales that gave the 40th parallels their reputation. The monsoon reversal of the northern Indian Ocean stood out clearly as a seasonal exchange. An earlier chart of the trade winds had been published by Edmund Halley in the 1680s, and George Hadley had proposed in the following century that heating at the equator and the turning of the earth together explained them. The ship's returns turned that reasoning into geography with edges and dates. Currents came into the same picture, since they were partly the wind's work. Benjamin Franklin, prompted by a Nantucket whaling captain who knew where the warm water ran, had published a chart of the Gulf Stream in the previous century and taken sea temperatures on his crossings to trace its margin. Thermometer readings from merchant ships now filled in the great looping circulations of each ocean basin, warm on the western sides, cool where water rose along eastern coasts, and drift bottles thrown overboard and recovered years later on distant beaches added crude confirmation. The correspondence between the belts of wind and the loops of water was too close to be accidental, though the mechanics of how a steady wind drags an ocean into a gyre would occupy theorists for another century. None of this material was clean. Wind force was estimated by eye. Positions were fixed by dead reckoning as often as by observation, and prudent captains steered around the worst weather, which left the record systematically short of the storms that had been avoided. Ships kept to lanes, so vast stretches of the southern oceans were sampled thinly or not at all. Those limitations are still being worked around by researchers who photograph and transcribe old logbooks into databases, from which the pressure patterns of particular vanished winters can be partially reconstructed, and from which the winds of the 1850s can be compared with those of a century later. Electricity altered the terms of the problem in a way that nothing before it had. Until the middle of the 19th century, news about the weather traveled at the speed of a horseman, a coach, a ship, or a signal fire, which is to say at roughly the speed of the weather itself, and often rather slower, so a gale arriving on a coast was the first announcement of its own existence. A depression crossing Western Europe moves at something like 30 or 40 kilometers an hour, sometimes faster, and a rider could not reliably outrun that over any useful distance. A current sent along a copper wire, by contrast, arrives for practical purposes at once, and this meant that a town could be told what had already happened, 500 kilometers upwind, while there was still time to do something about it. Telegraph lines spread first for other reasons entirely, along railways where they regulated traffic and prevented collisions, and between cities where merchants and newspapers were willing to pay for prices and headlines. Samuel Morse's line between Washington and Baltimore opened in 1844, and in Britain the apparatus developed by William Cooke and Charles Wheatstone was already running beside the tracks out of London. Within a decade, the wires formed a mesh dense enough that weather reports could ride on them almost as an afterthought, filling idle minutes in the operating rooms. And the men who saw this possibility spent much of their energy persuading telegraph companies to carry such messages cheaply or without charge, on the grounds that the resulting knowledge was a public good. During the Great Exhibition in London in 1851, visitors could buy a daily map of the weather over Britain, compiled from reports sent in by wire that same morning and printed on the spot. James Glaisher of the Greenwich Observatory was behind the arrangement, and the sheets carried the ordinary business of a modern chart in embryo, with the state of the sky, the direction of the wind, and the readings of the barometer set down beside the names of the places they came from. Nobody claimed to predict anything from them. They were a portrait of a single hour across an entire country, which had never been drawn from fresh observations before, and simply having such a thing in the hand made the atmosphere look less like local caprice and more like a single moving system. Across the Atlantic, Joseph Henry, the first secretary of the Smithsonian Institution, had begun assembling something similar from the late 1840s, negotiating with telegraph companies to transmit morning observations from a growing list of correspondents. In the entrance hall of the Smithsonian Building, a large map of the United States was fitted with small discs that could be changed each day, showing where the sky was clear, where it was overcast, and where rain or snow was falling, so that visitors saw the continent's weather laid out as of that morning. The pattern that emerged from such displays was a slow drift of conditions from west to east across the country, which was already suspected but now became something a person could watch. The American Civil War cut the network's lines and its funding, and the display lapsed. A single disaster did more than any argument to make the case in Britain. On the night of the 25th of October, 1859, a violent storm caught the steam clipper Royal Charter on the coast of Anglesey, close to the end of a voyage from Australia, and she broke up with heavy loss of life, along with many other vessels around the British Isles in the same few days. Robert Fitzroy, who had commanded the Beagle on her surveying voyage, and now ran the small meteorological department of the Board of Trade, reconstructed the storm's track from later reports and concluded that it had been observable in its early stages from places where the telegraph reached. From February of 1861, his office began sending warnings to ports, where harbour masters hoisted a canvas cone on a mast, point upward for a gale expected from the north, and point downward for one from the south. Later the same year, Fitzroy went further and supplied the newspapers with short statements of the weather expected over the following 2 days. He chose the word forecast with care, and said so in print, wanting a term that suggested a calculation made from present conditions rather than a prophecy pronounced over the future. And the distinction mattered to him because almanac makers and self-appointed weather prophets were already numerous, and the new department's respectability was thin. His notices were brief, cautious, and frequently wrong, and he was attacked from 2 directions at once, by scientists who thought the physics far too immature to support any such public statement, and by ship owners who resented warnings that kept crews in harbour on days that turned out fine. Fitzroy died in 1865, worn down by overwork and by the controversy, and the forecasts were discontinued shortly afterwards, though the storm warnings proved too useful to abandon and returned within a few years, with published forecasts following later in the 1870s. France arrived at the same place by way of a naval catastrophe in the Black Sea. On the 14th of November 1854, during the Crimean War, a gale struck the Allied fleet off Balaclava and wrecked a number of ships, and the French authorities asked the Paris Observatory to look into it. Urbain Le Verrier, an astronomer whose calculations had helped locate Neptune, wrote to observers across Europe for their records of those days, and the collected replies showed a storm that had crossed the continent from the west along a traceable path over several days, passing near places connected by telegraph well before it reached the fleet. His conclusion was that a permanent network of daily telegraphic reports would have allowed a warning, and from that argument grew the French observation service and eventually a printed international bulletin issued from Paris, gathering readings from stations in several countries. The charts drawn from these reports acquired the name synoptic, from a Greek word for seeing together, since their whole purpose was to place many simultaneous observations in one view. Simultaneity turned out to be the demanding part. Observers had to read their instruments at agreed hours by an agreed clock, correct their barometers for temperature and height above sea level, and compress the result into a few words, since telegraph charges and transmission time both rewarded brevity, which is why elaborate codes were devised in which a handful of letters or figures stood for pressure, temperature, wind, and the state of the sky. At the central office, a clerk plotted the incoming figures on a blank map, and someone then drew by hand the lines connecting places of equal pressure, the isobars, which closed into loops around the centers of high and low pressure. Once those loops were visible, regularities appeared that no single observer could have found. Christophorus Buys Ballot, working in the Netherlands, set out the relation between wind and pressure in a form simple enough to be memorized by any sailor, namely that in the northern hemisphere, a person standing with their back to the wind has the lower pressure on their left. Forecasters learned that the closer the isobars crowded together, the stronger the wind, and that the low-pressure centers of middle latitudes tended to travel with a general eastward drift, so that a chart plus a ruler plus experience of how such systems had behaved before, yielded a serviceable guess about tomorrow. It was empirical throughout, a craft of pattern recognition rather than a deduction from the laws of motion, and its practitioners knew as much. In the United States, the initiative revived after the war, partly through Cleveland Abbey, who issued daily bulletins from an observatory in Cincinnati from 1869 using telegraphed reports. In 1870, Congress assigned the work of storm warnings to the Signal Service of the Army, which had the discipline and the wires to take simultaneous readings across a continent, and shipping on the Great Lakes was among the first beneficiaries. International coordination followed, and a Congress of meteorologists met in Vienna in 1873 to settle observing hours, units, symbols, and telegraphic codes, since a chart assembled from national data was only as coherent as the agreements behind it. What the maps could not show remained considerable. Over the Atlantic, there were no stations at all, so European forecasters watched weather arrive from a blank space, and the whole picture was flat, a single sheet of pressures measured at the ground, with the depth of the air above it left entirely to inference. Height was the missing dimension, and for most of human history the only way to gain any of it was to walk uphill. Mountains served as the first observatories of the upper air, and by the later 19th century several countries had built stations on summits and staffed them year-round, at Ben Nevis in Scotland, on Pikes Peak in Colorado, on Mount Washington in New England, where observers wintered in stone huts and recorded pressure, temperature and wind at heights no valley station could reach. Their logbooks were valuable, and they were also misleading in a way that took some time to articulate clearly. A mountain, after all, is not simply a marker placed in the free atmosphere. Its rock absorbs sunlight and warms the air in contact with it. Its slopes generate their own breezes that rise by day and drain downward at night, and its bulk deflects the wind that would otherwise pass smoothly through that level. A thermometer on a summit measures the mountain as much as the sky. To learn what the air was doing 3 or 4 kilometers above flat ground, the instruments had to be carried up into air that touched nothing at all. Ballooning made that possible within a few months of its invention. When Jacques Charles ascended from Paris in a hydrogen balloon in 1783, he took a barometer and a thermometer with him and remarked on the cold and on the swiftness with which the barometer fell. And the following year, the American physician John Jeffries went aloft with Jean-Pierre Blanchard, carrying instruments and sealed flasks in which to trap samples of high air. The spectacle of flight attracted crowds, and the crowds paid for the gas. But attached to almost every early ascent was somebody with a notebook, watching a needle instead of the horizon. In the late summer of 1804, Joseph-Louis Gay-Lussac made 2 ascents from Paris, the first with the physicist Jean-Baptiste Biot, and the second alone, reaching something above 7,000 meters, a height that stood as a record for half a century. He brought back evacuated glass flasks that he had opened at altitude and closed again, and analysis showed that the composition of the air up there was essentially the same as the air at the ground, with the same proportion of oxygen. That finding was quietly important. It meant the lower atmosphere was thoroughly stirred, rather than sorted by weight into layers of heavy gas beneath light, and any theory of the sky had to begin from a well-mixed fluid. Cooling with height was the other consistent result, and it eventually acquired a physical explanation rather than merely a description. A parcel of air that rises finds itself under less pressure, expands against its surroundings, and in expanding does work and loses heat, so that dry air rising freely cools at close to 10 degrees Celsius for every kilometer gained. Where the air is moist, condensation releases latent heat and slows the cooling considerably, which is why the average observed decline through the lower atmosphere settles nearer 6 or 7 degrees per kilometer. Balloon ascents turned that from an argument into a measured curve. British interest in the vertical profile became systematic in the 1860s, when the British Association funded a series of scientific ascents flown by the professional aeronaut Henry Coxwell and observed by James Glaisher of the Greenwich Observatory. Glaisher took up thermometers, wet and dry bulbs for humidity, aneroid and mercury barometers, and a caged bird or two, and he published tables of temperature and dew point at successive heights that were used for decades afterwards. Their flight from Wolverhampton in 1862 became the best known of them, and also the most cautionary, since Glaisher lost the use of his limbs and then consciousness, and Coxwell, whose hands had frozen, pulled the valve cord with his teeth to bring the balloon down. The greatest height reached that day was never established with confidence, for the observer and his instruments failed together. Physiology set the ceiling, and the ceiling was learned at some cost. Paul Burt, working in Paris on the effects of reduced barometric pressure, showed experimentally that the danger lay not in the thinness of the air as such, but in the low pressure of oxygen within it, and he recommended that aeronauts breathe from bags of enriched air. 3 men who had taken his advice on an earlier flight went up in the balloon zenith in 1875 and rose beyond the point where their supply and their judgment held. Only Gaston Tissandier came down alive, and the deaths of his 2 companions marked the practical limit of unassisted human observation in the upper air. Oxygen extended that limit rather than removing it. In 1901, the German aeronauts Arthur Berson and Reinhard Söring reached somewhere near 10,800 meters in a large balloon over Berlin, breathing from cylinders and losing consciousness even so, and their flight stood for many years as the highest anyone had gone in an open basket. What became clear to the observatories was that the interesting question lay above the region a human body could tolerate, and that the answer would have to be brought back by something other than a person. Instruments, unlike lungs, do not object to cold or vacuum. From 1892, Gustave Hermite and Georges Besançon in Paris began sending up small unmanned balloons of varnished paper, later of rubber, carrying recording instruments and no crew, and the method spread quickly through the European observatories under the name of sounding balloons. Such a balloon rises until the falling pressure outside stretches its envelope past bursting, and the wreckage with its instrument package descends, sometimes under a small parachute, sometimes hanging beneath the collapsed rubber, into a field or a wood or the sea. Recovery depended on strangers, so the packages carried printed labels asking the finder to return them, occasionally with the promise of a modest reward. Each package held a meteorograph, a clockwork instrument small enough to be lifted by a few cubic meters of hydrogen. A sealed aneroid capsule expanded as the pressure dropped and moved a stylus across a drum turned by clock. A bimetallic strip curled with temperature and moved a second stylus, and a strand of human hair which lengthens slightly as humidity rises, worked a third. The trace was read after recovery, and pressure served as the record of height, so that the flight returned a continuous curve of temperature and moisture through the whole depth of air the balloon had crossed. From the observatory he established at Trappes, southwest of Paris, in 1896, Léon Tisserand de Bourg launched such balloons in the hundreds, and the curves he collected did something unexpected in their upper portions. Temperature fell steadily, as everyone expected, until a level somewhere near 11 kilometers over France, and then the fall stopped, and above that the trace ran nearly flat or even turned slightly warmer for as far as the instruments went. Suspecting that sunlight falling on the thermometer might be producing a false steadiness, he flew balloons at night and found the same flattening, and he announced the result in the first years of the new century. Richard Assmann, working in Berlin with large rubber balloons and instruments of his own design, reached the same conclusion independently and published at nearly the same time. Naming followed the discovery. Tisserand de Bourg called the lower region the troposphere, from the Greek word for turning, because it is the part of the air that overturns and mixes and carries the weather, and he called the region above it the stratosphere, on the supposition that in air so stable the gases might settle into strata according to their weight. The boundary took the name tropopause, and further soundings showed that it does not sit at a single height, lying near 16 kilometers over the tropics and dropping to perhaps 8 over the poles, with breaks and slopes between. The reason for the flattening, the absorption of ultraviolet sunlight by ozone concentrated in that upper region, was worked out in the decades that followed. Kites offered the other route upward, and for routine daily work they were in some ways the better one. At the Blue Hill Observatory outside Boston, founded by Abbot Lawrence Roche in 1885, observers flew trains of box kites of the pattern devised by Lawrence Hargrave in Australia, along with the tailless kites of William Eddy, lifting meteorographs on lines of steel piano wire wound from a powered reel. A kite can be held steady at a chosen level for hours, which a balloon cannot, and it comes back with its instrument attached. It also requires wind to fly, tends to reach only a few kilometers at best, and drops kilometers of wire across roads and telegraph lines when the line parts, which is why the kite stations that the United States Weather Bureau operated across the plains were eventually retired in favor of balloons and, later, aircraft. What all this vertical evidence changed was the shape of the atmosphere in the meteorologist's mind. The sheet of pressures drawn from ground stations became the lowest slice of something with structure and a lid, a stirred layer some 10 to 16 kilometers deep, in which clouds form and storms travel, capped by a stable region that flattens the tops of the largest thunderclouds into anvils and holds the weather beneath it. Inversions of temperature, once puzzling, explained why smoke sometimes spread sideways instead of rising and why fog persisted in valleys through a bright morning. The air had acquired a depth that could be measured, and with it the possibility of asking what the layers were made of and where each of them had been. Norway came out of the First World War with a weather service that had been half-blinded. Telegraphic exchanges of observations across Europe had been restricted or cut altogether during the fighting, and reports from the Atlantic, where the country's weather chiefly comes from, arrived thinly or not at all. Wilhelm Bjerknes, who had spent years arguing that the atmosphere could be treated as a problem in physics, moved to Bergen in 1917 and set about founding a geophysical institute there. He also secured support for something more immediately useful, a much denser network of observing stations along the Norwegian coast and through the inland valleys, justified by the needs of farmers bringing in hay and of fishing fleets working open water in small boats. The war had made food and fuel scarce, and a forecast that saved a harvest or a catch was worth paying for. Stations were spaced far more closely than any national network had managed before, and their reports came in several times a day to be plotted on charts by a small group of assistants, most of them very young. Jakob Bjerknes, the son of Wilhelm, was in his early 20s. Halvor Solberg was a few years older, and Tor Bergeron, a Swede, joined them soon after. Their work was largely the patient drawing of maps, hour upon hour of penciled isobars, wind arrows, temperatures and cloud symbols, and it was the closeness of the stations that made the difference. Where a sparse network smooths everything into gentle curves, a dense one records the sharp changes, and the sharp changes turned out to be where the weather lived. What the charts showed, once there were enough observations to reveal it, was that the changes of wind and temperature around a low-pressure area were not spread evenly through it. They were concentrated along narrow lines that swept across the country in a fixed order, with rain falling in bands rather than filling the whole cyclone, and with the wind at a given place turning abruptly rather than swinging round by degrees. The older textbook picture had a depression as a roughly symmetrical whirl, air spiraling inwards towards a center of low pressure and rising there to produce cloud and rain more or less all around. Observations from the Norwegian network fitted that picture badly, and fitted a different one well. Some of the ingredients had been prepared long before. Hermann von Helmholtz had studied surfaces of discontinuity in the atmosphere, boundaries where two currents of different density slide past each other, and had shown that such surfaces must slope rather than stand upright when the Earth's rotation is taken into account. Max Margulis in Vienna had calculated the energy available in a storm and found that it could be accounted for by the rearrangement of cold and warm air lying side by side, one sinking and the other rising. In Britain, Napier Shaw and Robert Lemfert had traced the paths of air arriving at a depression from different quarters, and found that the parcels came from widely separated origins with widely different properties. The pieces existed. What was missing was a single geometry that tied them to the daily weather map. In 1919, Jakob Bjerknes published a short paper on the structure of moving cyclones which supplied that geometry. A depression, in his description, was built around a tongue of warm air, pushing polewards into colder air, so that its southern half contained a wedge of warm, moist, often tropical air, bounded on two sides by cold air of quite different origin. Ahead of the warm tongue lay one line of discontinuity, which he called the steering line because the whole system tended to travel along it, and behind the tongue lay another, sharper one, which he called the squall line for the gusts and showers that came with it. The rain fell in two distinct areas, a broad shield ahead and a narrower band behind, with a slot of relatively clear and mild weather between them. A word was soon found for those lines. The Bergen group began speaking of fronts, taking a term that had been in every newspaper for 4 years, describing the long contested boundaries between armies in France and elsewhere, and applying it to the boundaries between bodies of air. Steering line became warm front, since the warm air advanced there, and squall line became cold front, where cold air pushed forward and undercut the warm. Whether the borrowing was deliberate homage to the language of the war or simply the readiest word available has been argued over since. But the choice stuck, and with it a habit of speaking about air in terms of advance, retreat, and encounter that meteorology has never given up. Physically, a front is a sloping surface rather than a wall. Cold air is denser, so it lies underneath, and the warm air rides up over it along a slope that is remarkably gentle, often something like 1 in 100 or 1 in 200 at a warm front, which means that the boundary reaches a height of several kilometers only after stretching hundreds of kilometers horizontally. That geometry explains the familiar sequence at a place lying in the path of an approaching depression, first high cirrus, drawn out in filaments, then a lowering, thickening sheet of middle cloud through which the sun shows as a pale disk, then continuous rain or snow from a grey base, then a rise in temperature and a veering of the wind as the front passes and the warm sector arrives. The cold front behind is steeper and narrower, with heaped cloud, a burst of heavy rain or hail, a sharp drop in temperature, and a clearing sky streaked with showers. 3 years after the first paper, Jakob Bjerknes and Halvor Solberg set the individual storm inside a larger scheme. They described a hemispheric boundary, the polar front, separating cold air of high latitudes from warm air of low latitudes, and showed that a small wave forming on that boundary could grow, deepen into a closed low, mature and then decay in a regular sequence lasting several days. Tor Bergeron supplied the last stage of the life cycle by describing occlusion, the process in which the faster-moving cold front catches up with the warm front, lifts the warm sector clear of the ground, and leaves the storm as a slowly filling vortex of cold air with its energy source cut off. Since one wave on the front tends to be followed by another, cyclones arrive in families, which is why unsettled weather in the middle latitudes so often comes in runs of 3 or 4 days rather than singly. Behind the fronts stood the air masses themselves, and here Bergeron did much of the classifying. Air that rests for many days over a source region takes on the temperature and humidity of the surface beneath it, so that a great pool of air lying over Siberian snow in winter becomes cold and dry throughout its depth, while air sitting over a subtropical ocean becomes warm and moist. A scheme of 2 pairs of adjectives followed, polar or tropical, for the temperature of the origin, maritime or continental for the moisture, giving a handful of basic types whose behavior could be anticipated. What mattered as much was modification in transit. Cold air crossing warmer water is heated from below, becomes unstable and fills with showers, while warm air moving over a cold sea is chilled from below, stabilizes and produces low stratus and sea fog. For a forecaster, the value of all this was that a chart of surface observations could now be read as a slice through a 3-dimensional structure. Locating the fronts allowed a prediction not merely that rain was likely, but of when it would begin, how long it would last, when the wind would turn, and by how much, and what would follow. The Bergen forecasts issued for the fishing fleets and the hay harvest were built this way, and the sparse upper air soundings then available, along with the mountain observations Norway had in abundance, tended to confirm the sloping surfaces the model required. Later radio sonde ascents taken in their thousands, showed the frontal zones directly as tilted layers of sharply changing temperature and humidity. Adoption elsewhere came slowly and unevenly. Established services had their own methods and their own senior men, and the new analysis demanded denser observations, more frequent charts, and a retrained staff. Through the 1920s and 30s, the ideas traveled with people who had studied at Bergen or been taught by those who had, and the growth of commercial aviation, which needed to know about cloud bases, icing and turbulence rather than simply tomorrow's rainfall, gave the method a constituency that could not be ignored. By the years around the Second World War, the frontal chart had become the standard working document of weather services across Europe and North America, with its lines of triangles and semicircles that survive on published maps to this day. Later work softened the picture without discarding it. Fronts are not surfaces, but zones, often tens of kilometers wide, sometimes vanishing and reforming. The polar front is not a single continuous seam around the hemisphere, but a discontinuous, shifting family of boundaries, and the growth of a depression is now understood through the interaction of the surface front with the wave patterns of the upper air, which the Bergen school could not yet see. What endured was the underlying change of mind. Air had ceased to be a uniform medium in which pressure happened to vary, and had become instead a collection of bodies, each carrying the imprint of the ocean or the ice or the desert where it had lain, meeting along boundaries where the weather of the middle latitudes is made. Above the fronts lay a region the Bergen analysts could reason about but never chart, and their maps, however carefully drawn, describe the bottom kilometre or two of an atmosphere 10 times deeper. Mountain observatories supplied a scattering of readings from 2 or 3 kilometres up. Kites had climbed higher in favourable weather, and manned balloons had brought back soundings from single afternoons in single places. None of it amounted to a daily portrait of the air at the height where the troposphere gives way to the stratosphere. That the upper westerlies existed was known from the drift of high cloud and volcanic haze. How strong they were and how they were arranged remained largely a matter of inference. At an observatory on the plain northeast of Tokyo through the 1920s, the Japanese meteorologist Wasaburo Oishi released small hydrogen balloons and followed them with a theodolite, recording the direction and speed of their drift as they rose. Above about 9 or 10 kilometers, he found westerly winds of an intensity that had no counterpart in the surface records, sometimes exceeding 50 meters in a second, persisting through the winter months and returning year after year. He published his results in Esperanto, a language he had adopted out of conviction, and the reports circulated among a small readership. For 2 decades, the strongest winds yet measured over the northern hemisphere sat in print, accurately reported, largely unread. Optical tracking of free balloons had built-in limits that no diligence could remove. A balloon disappears into cloud and the observation ends. So the technique worked best on clear days, which are not a representative sample of weather. Even in clear air, the target became a fading point of light, and the calculation of its height depended on assuming a rate of ascent rather than measuring one. Observers learned the trade nonetheless, working in pairs at either end of a measured baseline or singly with an assumed climb rate, and their pilot balloon reports filled the upper air columns of the interwar years with data that were real, useful and thin. Around 1930, the problem was attacked from a different direction by several people at once, working separately and with different components in the Soviet Union, in France, and in Finland. The idea common to all of them was to stop looking at the balloon and let the balloon speak. A small package carrying a temperature element, a pressure element, and a moisture element was slung beneath the envelope, coupled to a light radio transmitter, and the readings were sent down as a coded stream of signals while the instrument climbed through the layers it was measuring. Pavel Molchanov in Russia and Vilho Vaisala in Finland built such devices in these years, and the word radio sonde came into use for them. Once the instrument was expendable and its report arrived by radio, cloud ceased to matter, night ceased to matter, and a sounding could be made from the same station every day in any weather. Tracking the transmitter by radio direction finding and later by radar and by radio navigation systems gave the wind at each level as well, so that a single balloon returned a profile of temperature, humidity, pressure, and wind from the ground to well above the tropopause. Each ascent cost an instrument that was never seen again, which was accepted as the price of a daily measurement, and services began to compare the profiles of neighboring stations as they had once compared barometers. Soundings gathered from many stations at the same hour could be plotted on a chart of a chosen pressure level rather than a chosen height, and when enough of them existed, the shape of the flow aloft emerged. Winds increased with altitude through the troposphere and concentrated into a narrow, fast ribbon just below the tropopause. The ribbon lay above the zones where the horizontal temperature contrast at lower levels was sharpest, which is to say above the fronts. And this was no coincidence, but a consequence of the balance between pressure, temperature, and rotation that governs large-scale flow. Cold air to one side and warm to the other require a wind that strengthens with height, and the front and the current above it are two aspects of a single structure. Wartime flying turned the matter from a research topic into an operational obstacle. When American bombers began high-altitude missions over Japan in 1944, crews flying westward at around 10 kilometers found their progress over the ground reduced to a crawl by headwinds far stronger than anything in their training, while eastbound legs ran at speeds that made accurate bombing difficult in the other direction. The winds Oishi had catalogued were being encountered by aircraft that had no choice but to fly in them. Navigators learned to plan for them, forecasters were asked to predict them, and the upper air chart acquired a constituency of pilots. Balloons of another kind crossed the same current at the same time, released from the Japanese coast and carried eastward on a journey of several days to the far side of the Pacific. Several thousand were launched, engineered to hold altitude by venting gas and dropping ballast. And a modest number reached North America, coming down in forests and fields from Alaska to the western United States. One that fell in Oregon killed 6 people who found it on the ground. Considered only as a physical demonstration, the flights confirmed that the flow aloft was continuous enough and swift enough to convey an object across an ocean without human guidance. Naming followed the phenomenon rather than preceding it. A German meteorologist had used a term meaning jet current in the late 1930s for the fast cause appearing in high-level analyses, and the English words jet stream settled into general use during and just after the war. Once the current had become a thing that many people needed to discuss. The image is imperfect. since nothing confines the flow as a nozzle confines a jet, but it conveys the essential fact of concentration, not a broad westerly drift across the hemisphere, but a meandering thread of high speed embedded within a slower stream. Carl Gustav Rossby, a Swedish meteorologist who spent his most productive years in the United States before returning to Stockholm, supplied the framework in which the upper flow made sense. Treating the westerlies as a shallow fluid on a rotating planet, he showed that because the effect of rotation varies with latitude, any north or south displacement of the current generates a restoring tendency, and the flow responds by oscillating in long horizontal waves. Their speed depends on their length. Short waves travel eastward with the current, while the longest waves move slowly or even drift westward against it. Typically 3 to 6 of these waves encircle the hemisphere at any time. In the wave picture, the surface weather acquires a steering mechanism. Troughs and ridges in the upper flow determine where air converges and where it spreads apart aloft, and a depression at the surface deepens where the divergence above it removes air faster than the surface convergence supplies it. Depressions travel along the flow beneath the current, families of them following the same track for days. When a long wave becomes large in amplitude and nearly stationary, a blocking pattern forms and the usual procession of systems is diverted, giving the persistent spells of dry heat, cold, or rain that had always been noticed and never explained. A jet stream, described in the plain terms of the soundings, has a core between roughly 9 and 12 kilometers above the surface, a width of a few hundred kilometers, a depth of only 2 or 3, and a length that can run for thousands. Speeds in the core commonly reach 100 to 200 kilometers per hour, and in winter can exceed 300. 2 principal currents occupy each hemisphere, one associated with the polar front and one nearer the subtropics, both stronger in winter, both shifting toward the pole in summer, and neither behaving as a fixed channel. They wander, split, weaken, and reform. After the war, the sounding network was organized as a global routine, with balloons released simultaneously from several hundred stations at the standard hours of midnight and midday by universal time, and often at the intermediate hours as well. A typical flight climbs at about 5 meters a second for an hour and a half or more, reporting continuously until the envelope bursts somewhere above 30 kilometers and the instrument descends on a small parachute into whatever lies below. Constant level balloons designed to drift for weeks at a fixed density surface, tracked from satellites, later filled some of the gaps over the southern oceans, and reports from commercial aircraft now thicken the upper air record along the busiest routes. Wilhelm Bjerknes had set out the idea plainly in 1904, in a short paper arguing that forecasting could be treated as a problem in physics rather than an art of resemblance, and his statement of it was almost austere. If the state of the atmosphere at a given moment were known with sufficient accuracy, and if the laws governing the way that state changes were known with sufficient completeness, then the state at any later moment followed as a matter of calculation. He listed the quantities that would have to be tracked: pressure, temperature, density, humidity, and the 3 components of the wind, and he named the equations that connected them, drawn from hydrodynamics and thermodynamics. What he did not have, and freely admitted he did not have, was any practical means of doing the arithmetic. Lewis Fry Richardson, an English physicist of Quaker conviction, who had worked for the Meteorological Office and who left it during the First World War rather than take up military duties, undertook the arithmetic anyway. He served instead with an ambulance unit in France, driving wounded men between dressing stations and field hospitals, and in the intervals between spells of duty, he carried out by hand a single trial calculation of the future weather over Central Europe. By his own account, the manuscript was lost during fighting in 1917 and recovered some months afterwards beneath a heap of coal. The finished work appeared in 1922 under a title that promised nothing beyond its contents, Weather Prediction by Numerical Process, and it sold very slowly. His method was the one still in use, reduced to its bones. He divided the atmosphere over the region into a checkerboard of columns roughly 200 kilometers across, cut each column into 5 layers by pressure, and assigned to every box a value for wind, temperature, pressure and moisture, taken from the observations gathered at 7 in the morning on the 20th of May, 1910, when balloons had been released across Europe as part of an international program. From those values he computed, box by box, the rate at which each quantity was changing, then advanced the whole field forward by a step of time and prepared to repeat the process. In practice, the labor was such that he completed the calculation for only 2 boxes and a single 6-hour step. The answer was wrong in a way that would have discouraged most people. Richardson's arithmetic gave a rise in surface pressure of about 145 millibars over 6 hours, a change larger than anything the atmosphere produces where the real pressure that morning had barely shifted. His procedure, examined decades later, turned out to be sound. The difficulty lay in the starting values and in the size of his time step. Observed wind and pressure fields never quite balance one another, and the small residual mismatch in his data set off large and rapid oscillations in the computed air, spurious waves that swamped the slow, meaningful evolution he was trying to follow. Techniques for smoothing initial data and a stability condition relating the length of a time step to the spacing of the grid, formulated in 1928 by Courant, Friedrichs and Louis, both came afterwards. Richardson also worked out what it would cost to keep pace with the weather instead of falling behind it, and described the result in a passage of sober fantasy. He imagined a great hall, tiered like a theatre, its walls painted with a map of the globe, filled with human computers, each responsible for one part of one equation over one region, passing intermediate results to their neighbors and receiving corrections from a director on a raised platform who coordinated the whole by colored signals. 64,000 people, by his estimate, would be needed to compute the weather as fast as it actually came. He added, with some regret, that this scheme lay too far beyond the means available to be worth pursuing, and turned his attention to other subjects, including the mathematics of conflict. Electronic calculation altered the arithmetic before it altered the meteorology. At the Institute for Advanced Study in Princeton, John von Neumann identified weather prediction as a problem well suited to the machines then being built, difficult enough to be interesting and bounded enough to be attempted, and gathered a small group of meteorologists to work on it. Jules Charny, who led the scientific side of that effort, made the decisive simplification. Rather than solving the full equations of motion, which permit sound waves and gravity waves, and all the fast oscillations that had wrecked Richardson's trial, he derived a filtered set in which those motions were removed by construction, leaving only the slow, rotating, large-scale flow that carries weather systems along. The simplest version tracked a single quantity, the vorticity of the air on one mid-tropospheric surface. On the ENIAC at the Aberdeen Proving Ground in Maryland, in the spring of 1950, Charney, Ragnar Fjørtoft, and their colleagues ran 4 24-hour forecasts of the flow over North America, using punched cards for input and output and a machine with less memory than a modern pocket calculator. Each forecast took roughly a day of running time once the handling of cards was included, so the computation and the weather advanced at about the same rate, and no forecast was ready before the atmosphere had already answered. The results were coarse and in places clearly mistaken, but the broad pattern of troughs and ridges moved and deepened in a way that resembled what had actually happened. That resemblance was the point. Sweden made the first regular real-time forecasts by computer in 1954, using a machine in Stockholm and a model in the same filtered family, and the United States established a joint numerical weather prediction unit the following year, with Britain and Japan and others following through the later 1950s. Once the machines were fast enough, the filtered equations were gradually abandoned in favor of the fuller set that Richardson had used, now stabilized by proper initialization and short time steps, and the grids grew finer while the number of vertical layers multiplied. Processes too small to appear on any practical grid, among them individual convective clouds, the turbulence of the lowest few hundred meters, the absorption of sunlight by water vapor, and the drag of hills had to be represented by formulas describing their average effect. An art known as parameterization that remains a large part of the work. Edward Lorenz at the Massachusetts Institute of Technology was investigating whether statistical methods could match the new numerical ones when he noticed something in the output of a small computer model he had written to imitate atmospheric convection. Restarting a run from figures he had copied down to 3 decimal places rather than the 6 the machine held, he found the new sequence tracking the old for a while and then diverging until the two bore no relation to each other. In a paper of 1963, working with the system of only 3 equations, he set out the general property behind that behavior. A set of deterministic equations can be so sensitive to its starting values that any error, however small, grows until the forecast is useless, and no improvement in the equations removes the limit. Predictability, understood in these terms, is a matter of how fast small errors double. In the atmosphere, the growth rate varies with the situation and the scale of the motion, and small features lose their identity within hours, while the large planetary waves keep some memory for a week or more. Practical skill in daily forecasting now extends to somewhere between a week and 10 days for the broad pattern, with useful detail in the first 3 or 4, and the theoretical ceiling for weather of the kind that appears on a chart is generally reckoned at about 2 weeks. Improvements in observation and computing have pushed forecasts closer to that ceiling, gaining roughly 1 day of accuracy per decade over the past half-century, without moving the ceiling itself. Rather than issue a single calculation and hope, forecasting centers from the early 1990s onward began running many, each starting from slightly different initial conditions or using slightly different physics and reading the spread between them as a measure of confidence. When the members of such an ensemble stay close together, the forecast can be stated firmly. When they scatter after 2 days, the uncertainty is real and is reported as a probability. A stated chance of rain of 60% means that in a large number of similar situations, rain fell in about that fraction of them, which is a more honest account of what the arithmetic can supply. Beyond the limit of individual forecasts, the averages remain calculable, so the seasons, the monsoons, and the long climatic means stay open to computation, even where tomorrow afternoon eventually does not. Photographs taken from small rockets in the late 1940s gave the first hint of what the atmosphere looked like from outside it. Cameras carried above New Mexico on captured wartime rockets returned grainy strips of cloud, stitched together afterwards into mosaics, and in those mosaics meteorologists could see arcs and swirls whose scale no ground station could have registered, because a network of surface reports gives points, and the photograph gave the shape between them. For a century and a half, the chart had been an inference, a pattern drawn in isopleths between numbers, and the rocket pictures suggested that the pattern might one day simply be looked at. That possibility arrived on the 1st of April, 1960, when a satellite named Tyros for television and infrared observation reached orbit and began transmitting pictures of cloud fields to receiving stations below. Its cameras were crude by any later standard. Its orbit was low and its lifetime was measured in weeks, and yet within days it had shown a mid-latitude depression as a broad comma of cloud with a trailing tail, which is very nearly the shape the Norwegian school had drawn from surface reports 40 years earlier. Confirmation of that kind is quieter than discovery, and in some ways more useful, since it told forecasters that the model in their heads corresponded to something they could now see whole. 2 families of orbit came to divide the work between them. Satellites in low polar orbits, a few hundred kilometers up, and timed so that they cross each latitude at roughly the same local hour each day, sweep the whole planet in strips twice daily, and see it at close range with fine detail. Satellites placed in the equatorial plane at about 35,800 kilometers circle once per day and so hang above a fixed longitude, watching one great disk of the Earth continuously. From 1966 onward, images from that high vantage were assembled in sequence, and the resulting loops let observers watch clouds move, which meant that the displacement of a cloud between frames could be converted into a wind at whatever height the cloud occupied. Visible light gives nothing at night, so infrared channels became the second eye. Every surface and every cloud top radiates according to its temperature. And since temperature in the troposphere falls with height at a fairly regular rate, the brightness of a cloud top in the infrared is a measure of how high it stands. Cold means tall, and tall usually means vigorous, so tropical thunderstorm clusters that in visible light look like white blotches resolve in infrared into cores that reach almost to the tropopause. A channel tuned near the strong water vapor absorption around 6 7/10 of a micrometer added something stranger still, an image of moisture in the middle atmosphere where no cloud exists, showing dry slots and moist plumes curling around each other in cloudless air. Imaging was only half of what the instruments could do. By measuring emitted radiation at several wavelengths within the carbon dioxide absorption bands, each of which comes from a slightly different depth in the atmosphere, a sounder can be made to yield an estimate of temperature at successive levels, so that a vertical profile is recovered without anything being flown through the air itself. Retrieving a profile from a handful of overlapping radiances is a mathematically awkward problem, since many profiles fit the same measurements, and the solutions depend on statistical assumptions about what atmospheres normally look like. Microwave sounders, added later, penetrate most cloud, and a further technique measures how radio signals from navigation satellites bend as they graze the limb of the atmosphere, since the amount of bending depends on density and thus on temperature and moisture along the ray. Numerical forecasting absorbed all of this, though not immediately and not easily. Early attempts converted satellite radiances into pseudo-observations of temperature and fed them in as though they had come from a radio sonde, with mixed results, and the more successful approach, developed through the 1980s and 1990s, was to let the model calculate what radiances it would produce and adjust its own state until the calculation matched what the satellite had actually measured. Under that arrangement, the great majority of the observations now entering a global forecast come from space, and the largest single gain has been in the southern hemisphere, where oceans cover most of the surface and the old network was thin enough that forecasts there once lagged years behind their northern equivalents. Seen continuously and as a whole, the atmosphere also turned out to contain features that fragmentary observation had underestimated. The band of convection near the equator proved to be a nearly unbroken ring of cloud clusters, shifting north and south with the seasons rather than sitting on the line. Dust lifted from the Sahara was tracked across the Atlantic in coherent plumes. Smoke from forest fires was followed for thousands of kilometers, and the low overcast that sits off subtropical western coasts revealed itself as a sheet of remarkable extent and sharp edges. Instruments measuring backscattered ultraviolet light provided the record against which the springtime loss of ozone over Antarctica, first reported from ground measurements in the mid-1980s, could be mapped in its full extent. Meanwhile, the same physics and much the same hardware were carried to other planets, where they found weather that no one had been in a position to describe. Mariner 4 returned the first close photographs of Mars in 1965 and found a cratered, apparently static world. 6 years later, Mariner 9 arrived in orbit and found the surface hidden almost entirely by a dust storm that had grown to encircle the planet, so that for weeks the cameras recorded a featureless ochre haze with only the tallest volcanic summits protruding through it. Waiting for the dust to settle was the first practical lesson in planetary meteorology. Mars, once it could be watched through a full year, showed a circulation driven by the same ingredients as the Earth's and dominated by an effect with no terrestrial parallel. Its air is mostly carbon dioxide at a pressure less than 1% of ours, and each winter a substantial fraction of that air freezes onto the polar cap, so that the total mass of the atmosphere rises and falls through the year, and surface pressure at a fixed site varies by roughly a quarter. Dust suspended in this thin air absorbs sunlight and warms the layer that holds it, which strengthens winds and lifts more dust, and the regional storms that appear most years occasionally grow until they cover the planet. Venus presented an atmosphere so unlike expectation that its behavior took decades to accept. Ultraviolet images returned in 1974 showed the cloud markings sweeping around the planet in about 4 days, while the solid body beneath turns once in 243 days, and in the opposite sense to its orbital motion, a wholesale super-rotation of the air that theory still works to reproduce in full. Beneath the sulfuric acid clouds, probes that survived the descent reported a surface pressure some 90 times terrestrial and a temperature near 460 degrees Celsius, uniform from equator to pole and from dayside to night. Jupiter and Saturn, having no surface, offered circulation without geography. The Voyager encounters of 1979 assembled time-lapse sequences from which winds could be measured directly by following cloud features, revealing alternating eastward and westward jets arranged in bands, with the Great Red Spot rotating between two of them as an oval that has been observed telescopically for well over a century. Saturn's northern pole was found to hold a persistent hexagonal wave in its jet, and its clouds occasionally erupt in a bright storm that spreads around the planet. Titan, wrapped in nitrogen haze, was shown to have methane clouds, methane rain, and standing lakes near its poles, a slow condensation cycle built from a different liquid. Farther out, Voyager 2 found Uranus and Neptune to be moving faster than their dim illumination suggested, with Neptune carrying winds near 2,000 kilometers per hour and dark oval storms that came and went between observations. Comparison of these cases has become its own discipline, since the equations that govern rotating, heated, condensing atmospheres are the same everywhere, and only the parameters change, so that a model written for the Earth can be given a different radius, a different rotation rate, a different condensable gas, and asked to reproduce what the spacecraft saw. Where it fails, the failure usually points at something imperfectly understood at home as well. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well, and see you very soon.